Last week, we were talking about how to make a theory for the magnitude of nematic order, and in particular, a theory to determine um, um, where's the isotropic nematic transition, right? How does a system go from having no nematic order to having some? And I suggested then that there were different kinds of approaches, right? That we could take either a macroscopic symmetry-based approach or develop a more microscopic theory that would depend on specific interactions among the molecules. So we got started with the macroscopic theory, which is called Landau de Gennes theory. And that's what I want to follow up on today. Okay, so what I am showing here is the last slide on the blackboard, the whiteboard from last week. Okay, and so you remember here the idea in Landau theory in general, in this kind of symmetry-based approach, is that we want to figure out, how can the free energy possibly depend on the order parameter? And we're making the assumptions that the order parameter is small, so that we could write the free energy as a power series in the order parameter. And that will make it to be a nice smooth function, even when the order parameter changes from 0 to something non-zero. So this is how we got started with that. Okay, so we started with writing out the free energy density, that is the free energy per volume. And that is a constant. Then there's no term that can be first order in the order parameter. There's nothing that we could construct with the right symmetry properties to go there. And then there could be something that's second order in the order parameter, something third order, a couple possibilities that are fourth order. Let's stop there. Okay, so now the next step in the logic is to say, suppose this tensor order parameter, the Q alpha beta, is related to the magnitude and direction of the nematic order. What does that do in the free energy? Okay. So let's concentrate on this second order term for the moment. Okay, so I'm going to copy that to the next slide. Okay, we have this second order term. All right, so now suppose that we have our Q tensor as the magnitude of nematic order S times this 3/2 n alpha n beta minus a half delta alpha beta. So this piece has to do with the magnitude, and all this stuff has to do with the direction of the nematic order. Okay, now let's figure out what is this term in the free energy, the Q alpha beta, in terms of the magnitude and direction. Okay. So we'll substitute in Q alpha beta is this thing, S times 3/2 n alpha n beta minus a half delta alpha beta. Okay, contracted with another copy of the same thing. Okay, so 3/2 n alpha n beta minus a half delta alpha beta. Okay, let's simplify this expression. So there's an s squared in the front. Now, here's just a little practice in manipulating tensors. I guess I'll do this once. So we want to multiply out all these different terms. Okay? So if we multiply the first times the first, that gives us 9/4 n alpha n alpha n beta n beta. Okay. Now n alpha, that is just n dot n, right? That's the dot product. N beta is also n dot n, the dot product. And n dot n is 1 because n is defined to be a unit vector. Okay? So this term is just 9/4. It's just a number. Now, what about a term like the first times the second thing? Okay. So that is minus 3/2 times 1/2. So minus 3/4 n alpha, n beta, delta alpha beta. Okay, we can simplify this, right? So the n beta contracted with delta alpha beta gives us just n alpha, right? Because the only non-zero term is when beta equals alpha, and then the delta is just 1, right? So it's just 1 times n alpha. And then n alpha, this is n dot n, so that's equal to 1. So this whole term is just 3/4, negative 3/4. Again, it's just a number, right? So let's see, that was the first times the second. Now we can do the second times the first. Well, that's just another copy of the same thing. So we'll say this times 2. Okay? And then we have the second times the second. Okay? So that gives us plus 1/4 delta alpha beta delta alpha beta. Right? So we can simplify this combination of tensors, right? Because when we contract the first delta with the second delta, we only get a non-zero piece when alpha equals beta. So that is equal to delta alpha alpha, which means delta XX plus delta YY plus delta ZZ. So that's equal to 3. Okay. Students often think it's equal to 1. It's actually equal to the dimension of space. So it's 3. Okay, so all of these things inside the parentheses are just numbers. So we can simplify them. It's s squared, 9/4 minus 6/4 plus 3/4. So that's s squared times 6/4. All right, so it's 3/2 s squared. Okay, so when we look at this second order term, right, this thing is going, this, what I'm circling, this is proportional to s squared, right? It's 3/2 s squared. And there's some unknown coefficient in there. So whatever is this unknown coefficient, I'm going to multiply it by 3/2 s squared. Okay, now we can do the same thing with the other combinations of tensors. And maybe I'll just save time by skipping to the answers there. Okay, so for the cubic combination, the Q alpha beta, Q beta gamma, Q gamma alpha, this all works out to be 3/4 s cubed. Okay, so I'm not going to go through this, but this would be a great final exam problem I could give to you. You can tell that it has to be something times s cubed because there's 3 factors of the Q tensor, and each factor of the Q tensor brings a factor of s, right? So it must be something times s cubed. And so all the tensor manipulation that you would do to simplify it, that will just give you the constant in front, the 3/4. Okay, and similarly for the 4th order terms, you could have a 4th order term like Q alpha beta times Q gamma delta, Q gamma delta. Okay, so that's equal to 9/4 s to the 4th, right? That's the square of the thing that I calculated for you on the last slide. And for contracting the indices like this, Q alpha beta, Q beta gamma, Q gamma delta, Q delta alpha, this all comes out to be 9/8 s to the 4th. Okay, so I can put all of these things into the power series that is written out here, okay, and express the free energy density express the free energy density in terms of the magnitude and direction of nematic order. Okay. So F is this 0th order term, constant. There is no 1st order term. Then there is a 2nd order term, which could be written as blank times 3/2 s squared, plus the cubic term, which is blank times 3/4 s cubed, plus, I don't know, 1 blank times 9/4 s to the 4th, plus another blank times 9/8 s to the 4th. Now, you know, I write all these blanks when there's a coefficient that I don't know or even especially care about, because you know, it saves the trouble of giving it a name. I wouldn't do this if I'm actually publishing an article, but you know, for presenting it out loud, it's like that. But for now, let's give these things names. Okay, so for this coefficient, blank times 3/2, let's call that 1/2 A. And here, the blank times 3/4, let's call that 1/3 B. And this blank plus this blank, well, let's call all of that stuff 1/4 C. So the free energy is the combination then, F0 plus 1/2 A s squared plus 1/3 b s cubed plus 1/4 c s to the fourth. In principle, there could be higher order terms also, but we'll forget about them for now. We'll neglect them for now. Now, of course, I could have labeled these coefficients as just a, b, and c without the little fractions, a half, a third, a fourth in front of them. I put the fractions there. It's kind of conventional for people to put the fractions there because it'll make some of the other calculations a little bit easier later on. But it's not hugely important. Okay, now this then shows how does the free energy depend on the magnitude of nematic order, that is on the S. You might be wondering to yourselves, wait a minute, didn't he promise he would show how it depends on the magnitude and direction of nematic order? How does it depend on the direction? Okay, and the answer is just, it doesn't depend on the direction. Here, I'll write that out. Whoops, it doesn't depend on the direction, that is to say, on the director n, is independent of n. And that's an important point, right? The important point is that the free energy depends on the magnitude, but it's the same regardless of whether the liquid crystal is orienting, in one direction or along the z-axis or along the x-axis or in any other direction in three-dimensional space. Right? So the direction of nematic order is just going to be determined by spontaneous symmetry breaking, right? That the system can make nematic order in any direction. And so it will just pick a direction randomly. It's like with the Ising magnet, where it could make magnetic order pointing up or pointing down, and it just picks up or down randomly. Here it picks any direction in three-dimensional space randomly. All right, so now we could say here is an expression for the free energy in terms of S. And a good next step would be to plot this free energy and see what's the shape of the free energy as a function of S. And the result that we get, of course, depends on these parameters A, B, and C. So let's think for a minute about what we can say about these parameters. Well, one thing that's clear is that if we stop the expansion here at fourth order, then we need to assume that C is positive. Right? We must assume C is positive, right? What would happen if C were negative, right? Well, if C were negative, then when the order parameter S became very large, either large positive or large negative, then the free energy would become more and more and more negative, right? The system would be thermodynamically unstable because you could go to infinitely large negative free energy by going to larger and larger S. Right? That's impossible. Okay? So we must assume that C is positive. For A and B, we don't have constraints like that, right? A and B could be, in principle, either positive or negative, right? In most physical systems, it turns out that B is negative, okay? So I will say, I will assume B is negative for now. Later on, I will talk about what happens if B is positive. So suppose we want to make plots of this free energy. Okay, so I'll copy it onto the next page. Okay, so suppose we want to make plots of this thing, and we are going to assume that C is positive and B is negative. Okay. The kind of plot that we get has to depend, of course, on A. So I'm going to try what happens for different kinds of A, right? So let's now begin by saying, suppose A is large and positive. Right? In that case, let's plot the free energy F as a function of S. Well, it starts off at F0. Here, I'll draw this axis right here at free energy F0. Okay. When S is small, the dominant piece in this plot is going to be the AS squared piece, okay? For small s, S squared dominates over S cubed and S to the fourth. Okay? So for small s, we must have this kind of parabola curving upwards. Now, when S becomes larger, the S cubed term becomes important. Right? Remember, we're assuming that B is negative. Okay? So the BS cubed term is going to pull the function down a little when S is positive and push it up more when S is negative. Okay? Then when S becomes even larger, the CS to the fourth term is going to become important. And then the shape will be just pushed upwards. So we would expect to get a plot of the free energy that looks something like this. Okay. And in that case, we can see that the minimum is at S equals 0. Okay, this is the isotropic phase with S equals 0. Okay, now let's try reducing the value of A. Right? So here's plot number 1. Now I'll make plot number 2. reduce A. Of course, I could do this in Mathematica, but it's good to practice thinking about these things also, just even without using the software. Okay. So if we reduce A, now what happens? Right, well, again, we have a plot that starts off as a parabola. Now it's a parabola that's not so steep. Now, when we get to larger S, the term of BS cubed becomes important. Okay? So that makes a negative contribution when S is positive, and a positive contribution when S is negative. Okay? So over here, plot just goes up more. Over here, the plot might actually turn around and come down. Then when we get to even larger S, the CS to the fourth term becomes important. And then that's positive for both positive and negative S. So it makes the function look around something like this. So here you can see that there is a absolute minimum at S equals 0. That is the isotropic state. But there's also a local minimum at some positive value of S. Okay? So this is now a metastable nematic state. Okay, now let's continue to reduce A. All right, so I'll make plot number 3 down here. So for plot number 3, if we reduce A even more, the shape here is even a flatter parabola. And now, as I said before, right, when you get to larger S, you get a negative contribution over here from the BS cubed. And at a certain value, this just goes to 0. Whoops, it just goes to 0. Let me stop. It just goes to 0 right there. Over here, it keeps going up. Excuse me, it just goes to F sub 0. That's where this horizontal axis is. And then when you get to larger S, the S to the fourth term comes in and it makes the function go up. So here we can see that there are 2 equal minima there and there. This is then right at the transition, okay, between isotropic and nematic. So at this particular set of parameters, we're right at a first order transition where the system can jump from this state, isotropic, to this state, nematic. So it is a first order transition because there is a discontinuity in the order parameter. That is, it's not as if the minimum over here breaks up into different minima that have a tiny little bit of nematic order. Instead, this one becomes equal in free energy to this one, which has a substantial amount of nematic order. And then to draw one more plot, if we reduce A even more, we have a function for the free energy, which starts off going up a little bit. It's a parabola. And then it comes around, it becomes more negative over there. It gets to an even lower value of the free energy over there and goes up over here. And then the fourth order term turns things around. So the shape would look like this. And now the absolute minimum is over here. So the minimum, the absolute minimum, is at positive value of S. So this is in the nematic phase. And over here is a metastable isotropic phase.
Excuse me, may I ask a question?
Please, please.
Are you expanding the coefficient A about a temperature which is not the isotropic to nematic transition temperature? Because if you are expanding the coefficient A at the transition temperature, then A must be 0 at that temperature, right?
That's correct, right? That the transition does not occur when A equals 0, right? The transition occurs at a specific positive value of A.
Okay, thank you.
So the transition occurs, you can see where the parabola here has a certain curvature upwards, right? And this curvature depends on the coefficient A.
Okay.
So Ching's question is slightly ahead of what I was about to say, but let's get to that point, right? So the point is, right, here we have made a prediction for a transition from isotropic to nematic as a function of A. But you say, A? What's A? What good is a prediction that says there's a transition as a function of A, right? Well, the point is that A depends on temperature, okay? And that is familiar from the other examples of Landau theory that we have studied, okay? So we know that all of these arbitrary coefficients have some dependence on temperature. We don't know what it is, but there must be some dependence on temperature. So whatever it is, we could make a plot of it. We could say that A is changing like this, okay? It's varying somehow related to temperature. And B has some other dependence on temperature. And C has some other dependence on temperature. We don't know what they are, okay? But what we are finding is that there is a particular point where the isotropic nematic transition occurs, okay? That the isotropic nematic transition occurs when the curvature here is just right, right? Not too little, not too big, okay? It's a certain positive value. So that would be here, okay? So we could say that right here at this value of A, this is the value for the isotropic nematic transition. So that means that this temperature is the temperature associated with the isotropic nematic transition. Call that T sub IM. So this is similar to what we had for Landau theory with the Ising model, but the difference is that the transition is not occurring right at A equals 0. The transition occurs at A equals some specific positive number. So up till now, I've been speaking kind of schematically, okay, but we could also try to do things more algebraically, okay? So suppose we wanted to know what is the value of S in the equilibrium state. Okay? So we want to minimize this expression for the free energy, right? The expression right up here. Okay, so let's do that. Here, can I still paste? Yes, okay. So let's minimize this thing. Okay, so we want to say that the partial derivative of the free energy with respect to S is equal to 0. All right, that's an equation for a minimum or a maximum. Okay, so that means let's take the derivative. Okay, so A S, right, that's the derivative of the quadratic term, plus B S squared plus C S cubed has to equal to 0. You see that the numerical factors cancel because of the clever choice of fractions there, and there. That's why people do it. Okay, so this is a cubic equation to solve. Luckily, it factorizes. So we could say S equals 0 or A plus B S plus C S squared is equal to 0. And this is a quadratic equation, which we can solve, right? S is negative B plus or minus the square root of B squared minus 4AC all over 2C. So there are 3 solutions. That is totally reasonable because we can see in most of these plots that there's a min, a max, a min, right? Min, max, min, min, max, min. In this particular plot, there's only one min. That's where the thing inside the square root is negative. And so there's only one real solution, which is S equals 0. Okay, so that means the first of the solutions, the S equals 0, that's one of the minima. And then the solution with the negative square root, that's the maximum. And the solution with the positive square root is the second minimum. Okay? So we could say then that S equals 0. This is the isotropic solution. And the nematic solution is minus b plus square root b squared minus 4ac over 2c. Okay, now we could put each of those things back into the free energy to see what's the free energy of the isotropic solution and what's the free energy of the nematic solution. Okay. So if I put this thing into here, that gives us that F isotropic is just F0. If I put this thing into there, oh man, F nematic is equal to F0 plus 1/2 A times all of that stuff squared, plus 1/3 B times all of that stuff cubed, plus 1/4 C times all of that stuff to the 4th power. I don't really want to do that, but I could put it on your final exam or something like that. Okay, so yes, so this works, right? And it will give you some complicated expression for what is the free energy of the nematic phase in terms of A, B, and C. Right? Then, if you want to know where is the isotropic nematic transition, that transition would have to be where F isotropic is equal to F nematic. Right? So that corresponds to what we see in this plot number 3 over here, right? Where the isotropic free energy is just equal to the nematic free energy. So we can solve that, right? We can take this thing equal to this thing. And I'll skip to the answer. The answer is that this occurs when the parameter A at the isotropic nematic transition is equal to 2b squared over 9c. Okay, and you can calculate that for practice. Okay, and it also, then we could take this value of A and say, what is the order parameter on the nematic side of the transition, right? That is, we just plug that value of A into this equation. Okay. So, and S at that transition is equal to negative 2b over 3c. And remember that b is negative. And so this is a positive number. It's 2 times the absolute value of b over 3c. Okay, so this goes along with what I was telling you a few minutes ago, that the transition occurs at a specific positive value of the parameter A, not at A equals 0. Now, if we wanted to translate that into a temperature, we could say, well, let's assume that A depends on temperature as A prime times some T minus T0, where T0 is not necessarily the transition temperature, it's just whatever temperature it is where A equals 0. Right? And then the isotropic nematic transition will occur at A prime T minus T0 is equal to this thing, or 9C. So T is equal to T0 plus something, plus 2B squared over 9C A prime. Right? So the isotropic nematic transition temperature is not T0, it's T0 plus this positive offset. Okay. At this point, let's summarize what we've learned from this and then think about, was it worth it? Okay, so what have we learned from doing this calculation, right? The main thing I would say that we've learned from it is that the isotropic nematic transition is a first order transition, right? That it is different from the Ising transition from a paramagnet to the ferromagnet. Right? And so it happens with a series of plots like this one. And so it's a series of plots where the free energy, first it just has an isotropic minimum. Then it develops a metastable nematic minimum. Then at the first order transition temperature, the isotropic and nematic minima have equal free energy. And then at a lower temperature, the nematic goes lower than the isotropic. So this is the sequence of plots, assuming that C is positive, B is negative. If B were positive, by the way, you would have similar kinds of plots, but the nematic minimum would be over on the left side. It would be for negative S instead of positive S, somewhere over there. So that would be the weird case of a negative nematic order parameter, which doesn't occur in experiments very often. Okay, so that's, we've learned something from this. It wasn't a total waste, right? We've learned something in that just based on the symmetry of the order parameter, the fact that we have this second rank tensor order parameter, that tells us that the transition is first order rather than second order. That's interesting information to learn. Another thing that we learn is we can also learn about order induced by an applied electric or magnetic field. okay? That if you apply an electric or magnetic field, that this induces an order parameter which is proportional to E squared, or an order parameter which is proportional to H squared. That's different from the magnetic case, where the order parameter was linearly proportional to the field, or it's proportional to the first power of the field. So this is another interesting thing to learn, which is not obvious, and it just comes from the symmetry considerations. I don't have time to talk about all of this, but I will direct you to pages 145 to 147. Okay, so that's the good news. That's not bad for a theory which, you know, has no assumptions other than symmetry and smoothness of functions. But it's certainly not totally satisfying, right? It's not totally satisfying because it gives us our predictions in terms of parameters like A, B, and C, right? And so, you know, it's a further stretch to say, how are parameters like that related to experiments, right? In the lab, there is no piece of equipment with controls on it that are marked A, B, and C, right? You can't turn a knob and change A, right? And you can't tell a chemist to go in a lab and synthesize, you know, a liquid crystal with a bigger B, right? So these things are abstractions that are not directly tied to experiments. So that's one limitation of what we're doing. A second limitation of what we're doing here is that it predicts a temperature dependence for S as a function of temperature, which looks like this, okay? So it says that there's some temperature for the isotropic pneumatic transition, like that. And for temperatures above that, we have S equals 0. And then right at the transition, there's a discontinuity where we jump to the S that I calculated here, to this S, the 2 absolute value of B over 3C. Whoops, 2 absolute value of B over 3C. Okay. And then if we continue to reduce temperature, S continues to increase, and it curves over a little bit. But I will point out to you that this theory has no upper limit on S, right? That is, this kind of a theory doesn't know that the largest possible value of S is equal to 1, right? In this Landau style theory, S could just keep getting bigger and bigger as you go to lower and lower temperatures. And that's because this kind of theory is an expansion about S equals 0. And so it just doesn't carry with it the information about what's the largest value of S. It's based on small s. So this is a further limitation of the theory, right? And in this Landau de Gennes theory. So that is, these are reasons why we might want to consider a different style of theory that would complement this one, right? So a different style of theory that does make some specific assumptions about intermolecular interactions and then finds the free energy with mean field theory and minimizes it. So that is what I'm going to show you in the next class on Wednesday.